This is an introduction to exercise 6.6 on the graph of the derivative function. As in any number a, the gradient of the function at a equals to the height of the graph at f dash at a. Basically, what we're saying is we've got our original function, let's say f of x. When we find the derivative function, f dash of x, it's a general solution, so that when we substitute the value of x, we can get a specific value for the gradient. In this case, what I'm going to expect you to be able to do is to see a graph, something like this, hopefully a little bit more complex, and be able to draw the derivative function. Please note, the scaling of the derivative function can be very different from your original function. Typically, it's about the shape and key points or anchor points, and less so about specific values. Okay, so let's graph the derivative function for each one of these. This one's very straightforward. It's a linear equation. Right now, what's the gradient of our function? Guys, come on, this is like year 9. Sorry, what 1? Negative 1, thank you very much. It is negative 1, and I'm just going to draw a line across here, write that as dy dx, right? And of course, that's just going to be y equals to negative 1. Done, easy. Right? The gradient of this function, given it's a linear function, is constant. Therefore, it's just going to be a straight line across. Keep that in mind. This function here, what kind of function does it most resemble? Guys, we've got this. Cubic, thank you very much. It's a cubic function, right? When you derive a cubic function, what kind of function do you get? A parabola, a quadratic. So our derivative function should look like a parabola. I know that at that point of inflection, it has a point of 0 gradient. Therefore, at that point, I'm going to assume that that's at x equals 0. So, you know what? Yeah, let's assume that's x equals 0. So I'm going to do a dot there. As I go towards the right, towards a positive direction, my function starts off being 0, slightly positive, very positive, very positive. So it's going to look like this. Of course, alternatively, on the left-hand side, as my function goes from the very negative infinity towards 0, I'm going to end up with a function that's very, very positive, becomes less positive, reaches 0, and then it's a turning point. So a function will look like this. Again, you can see from a cubic to a parabola. Pretty straightforward? Great. Last example I'm going to go through here. Similar idea. Actually, is this the same function? This is the same function, but just translated somewhere. Again, this case, is that a stationary point? Well, let's start. Is it a point of inflection? Is it a stationary point? No. So, it is a... There we go. It is a stationary point. It's not a stationary point, but it is a point of inflection. So that is going to have to be reflected, no pun intended, in our derivative function. There is no value of 0. In fact, I'm going to, and again, it's approximation. It's a scaling issue, but as long as the shape of the graph is correct, it's fine. I'm going to assume that that gradient at x equals 0 is about 1. I'm going to say that's maybe here. Again, as I go towards the right, it's going to become more and more positive. As I go from the left towards the middle, it's going to be very positive, slowing down towards not 0, but it still looks like a parabola. Note that my function, or my derivative function, never reaches 0, because our original function of f of x, or of y, never has a turning point in this case. Any questions? No? Okay.